let's just make some plans about timing. So today, in the afternoon, maybe from 2 p.m. to 3:15 or something like that, I will give you the last remaining part about how to conclude about the convergence of the discrete functions f. You know, so the third part of proof of conformal invariance for easing by Smirnov. And then tomorrow, lecture as usual. Probably nothing in the afternoon, if you allow me. And then Wednesday will be there will be these it's sort of colloquium type lectures for IMPA in general. So one by Pierre and one by me in the afternoon. Okay, so let us remind us what we've done so far, and so I guess today's lecture will be the end of the cycle of the lectures on percolation, and then tomorrow, or maybe I'll start already today, to tell you some other stories, you know, about what is going on in other directions in this field. And of course, I will not be able to go into the same details, but I will try to be as clear as possible and complete as possible. Okay, so, but now we are still in the sort of part where we try to be understand everything and give details. So let us just remind sort of the structure of what we did so far. What we did so far. So what Vladas explained you at the very beginning was just, you know, the percolation model. Phase transitions. So there exists PC and the function theta of P, which was the probability that 0 is going to infinity, right? You use these notations, I believe. And so general stuff on percolation. And you know, when you do work on these two things, there are, you know, two main strange conjectures that you can state immediately. The first one is, you know, about the behavior of theta of P when P gets close to PC. And the second one is just, you know, about what happens at PC, so the probability that there exists. So there's this conjecture, you know, that in 2 dimensions, theta of P is like P minus PC to power 5 over 36 as P goes to PC plus. It's supposed to be true for basically all 2-dimensional regular periodic lattices. And the second conjecture is about, you know, what happens at the critical value, that the probability that 0, I don't know if you use this notation. So the probability that there exists an open path, you know, that the cluster of the origin has a diameter at least n. So you know that this decays to 0. That's part of these things, that there's no infinite exponent at d equal 2, but that this will decay like n to the minus 5 over 48 plus little over 1 as n goes to infinity. Right? And so it's easy to see, you know, using FKG, Russo-Seymour-Welsh type arguments, that this quantity will decay, cannot decay faster than 1 over square root of n or 1 over n, depending on what technique you use. and that it decays faster than some n to some alpha. Because in each annulus, you know, if you like look at this, say, take this n to be 2 to the power k, and each annulus between 2 to the k and 2 to the k plus 1, you have a positive probability to have a closed circuit that would prevent you to go further. So the fact that this will decay, you know, this is bounded by 2 powers of n when n goes to infinity is something fairly easy. And the question is to identify what the correct exponent is looks more complicated. Now, then you saw Smirnov-Cardy formula, right? That shows that for this specific grid, then you have the crossing probabilities, and actually more than the probability that of this guy, you know, D, A, B, C, X, that this would converge to X, where you have this picture. And this distance, right? So this was then, you know, the first identification of the understanding of some quantity when delta goes to 0, which means corresponds to the fact like when n goes to infinity, if you fix a lattice and let the size of the domains go to infinity, or if you fix a domain and let the lattice mesh go to 0. So that was the first, you know, the first, you know, entrance gate to these understanding of limiting behavior of these of percolation and connectivity properties. And there were two remarks, which were that, first of all, one important feature about this is that the limiting sort of quantity that you get here is a conformally invariant quantity, right? Because it is defined via conformal maps, and so two conformally equivalent domains will have the same, limiting crossing probability. And the second thing was, of course, that in order to prove it, you were using conformal invariance itself by, you know, trying to identify some discrete analytic function or almost discrete analytic function and understanding its scaling limit. So then what we defined was, you know, Loewner evolutions, Loewner chains, and so they are driving functions. So we understood, you know, how one could encode somehow curves, you know, that grow into the inside of a domain by just some one-dimensional functions and iterations of conformal maps, right? Sort of gamma corresponds to iterations of conformal maps. It corresponds to a driving function. We call W usually. Okay. And there was this picture that, you know, a driving function, continuous driving function constructs the Loewner chain. And the Loewner chain is not necessarily a curve, but something slightly more general, but that any curve corresponds to continuous driving functions. Okay. So then we combine these two things, right? These two ideas to say that, so to look at discrete exploration process. So that was, instead of just looking at the crossing probability, we took, you know, 2 points x and a, define the discrete exploration process gamma delta. Use a correct time parameterization, which is the one, you know, that the definition of Loewner chains tells you how to proceed. And what we ended up with was sort of basically the previous two items tells you the theorem that the discrete exploration process converges as delta goes to 0 to a random curve gamma that is also defined via a Loewner chain with driving function, so which is random, which is Wt is Brownian motion running at speed 6 times t. Okay? So, which means that we found out that in some way, you know, understanding already this equation, I mean, getting this, I mean, Cardy's formula for actually two different choices of the point C already allows you to identify the law of the entire curve, exploration curve, not only the limit of the crossing probability. So, which makes a big difference, because here we have only understood, you know, the limit of one number. And here we understand the limit of something much more complete that describes many things simultaneously because it's the entire curve. And this is nice because this is something you can compute things with. And so what we computed, so one can compute via SLE6. And so what we saw on Friday was that the probability that gamma up to the hitting time of the little circle here, so if we start something from here, so we had this, the probability that this up to this hitting time TR does not close a clockwise loop, right? That this was decaying like a constant, well, up to, we had this mod up to multiplicative constants, and when you can prove it up to constants, but that this, okay, I use this notion to say that what is on the right side and what is on the left side, the ratio between the two is bounded by, from above and from below, by positive finite constants. Right? So that, okay, I will say in a moment what I mean, so that this was decaying like r to the 5/48 when r goes to 0. So, you know, A, B means there exists constant C1 and C2 such that C1 A times C1 is smaller than B, smaller than A times C2. So it's not equivalent, but it basically says that at least the exponent is the right one. So when this was the definition where gamma was the radial exploration guy, you know, when you close an anti-clockwise loop, then you continue exploring to the inside. And then we had also the simpler guy, which was just, you know, that the exploration process doesn't close any loop. That this was decaying like r to the 1/4 as r goes to 0. Right? So these are computations that you perform directly in the SLE picture. And actually, maybe I show you another computation I mean, not another computation, but another result that you get in the same way. So I didn't detail this one, I just mentioned it. But maybe I can just draw you a picture. Suppose that you start the exploration process from here, and you are going to do the exploration process like this until you hit here. And then you are going to ask, when it hits the interior boundary, you're going to decide that you are going to bounce to the right. And you do this. And then you do something like that. So, of course, here maybe I should draw the picture like this. So you follow the following rule. You start from 1, you explore until you hit the interior boundary. So then you make as if the interior boundary would be orange. So that means you have to turn, right here. Then you go, therefore you go, up here and bounce on the blue again, and maybe you hit the circle again, and then you do as if the circle would be blue, and then you continue back here. So here you have a probability which is expressed in terms of exploration process, as before, as basically saying I take an SLE up to this hitting time, and then now I have a new domain which is a simply connected domain because this is now part of the boundary, and I start from here and I look at the probability that I hit, the other side here, and then I come back. So it's, gluing together 3 exploration processes as in the, the regular exploration case. And here what we ask is that you first go to the inside, then you go back to the outside, you go back to the inside without disconnecting. That means that this guy, for instance, it hasn't closed the loop, so you haven't, turned around and found your orange past at any time. So the probability of this, because of this SLE computation, you can prove that they correspond to, that this will decay like R to the, if this is R and this is R to the 5-fold. And this is, done in the following sense. Is basically first you have to cross to here, right? And now in the remaining domain, what you are looking for is an orange path and a blue path because you need a 2-color crossing. So that was the story I told you before, which was basically once you end up here, right? If we condition this, so we first end up here, conditionally on this picture, what is the probability that you will succeed in doing one more, back and forth crossing of this guy? Well, roughly speaking, the idea is to say, well, let us now look at this domain. Right. And what you want is, roughly speaking, the scaling limit of the percolation event that there exists here, an orange crossing here and a blue crossing there. Because if there exists an orange crossing here, that means that you have to, since you are bouncing on top of it, the curve gamma will have to go here or around here, and then now it will meet a blue one, so it will go here. And it will do all this before hitting the other part there. Right. So you have a very good estimate using SLE computation about, given this picture, so that you have this domain here, what is the probability to have roughly these 2 arms here? This is something you can compute. So what you're looking at is basically this quantity can be viewed as, expected value of the indicator function of this event times, the quantity which is basically measuring some sort of distance between this part and this part in this simply connected domain. So some number, some f of L, where L maybe is what we call the extremal distance here. So in other words, this domain here, you can map it onto onto this here, where the image of these 2 circles here would be sort of these endpoints, and if you say that this has height pi, then this length is what you call L here. And because of conformal invariance, you know that, so L is a conformal invariant quantity that describes this domain here, and sort of there's some sort of distance between this and this. And you know that the scaling limit, you know, when delta goes to 0, of the probability that there exist two crossings there is just a function of this quantity, and you can actually show that this is just e to the minus L. And then, so this is this type of thing, and you can look at my notes in various, either the one in Saint-Flour or Praxity or whatever. This is the type of thing you can compute using estimates about derivative of conformal maps, and you get indeed that this 4-arm quantity, and this event that you get back and forth like this. So of course here we don't have any blue and yellow arms, but it's just the probability that the SLE, the white SLE does this, that this will decay like r to the 5/4 as r goes to 0. So, and I don't want to give the details of that computation because it's very similar to what we did already. So these were SLE computations, right? So here I draw these colors, but the colors are actually not there because it's just a probability of SLE. So now what I want to explain is basically how you can go back from these three statements about SLE to the original percolation picture. So let us first look. So let us prove now the first one, which is the simplest, the following theorem about critical percolation. So which is that the probability that if I take critical percolation on mesh size 1, that there exists an open path from the origin all the way to distance n, that this decays like n to the minus 5/4. So actually the statement is, the rigorous statement is like that. This is what we can prove, which shows that 5048 is the right exponent, but is not as strong as we might hope for. Because we might say, well, okay, this probability is, bounded away by constants, say, from n, 1 over n to the 5/48. Right? So you see there are different, there would be different statements that are more sort of, I'm going to write statements that are weaker and weaker. First statement about function f would be f of n, is equivalent to constant times n to the 5/48 as n goes to infinity. The second statement would be, say, f of n is up to constants away of n to the 5/48. Right? That means might oscillate, between n over n to the minus 5/48 and 2n over to the power minus 5/48. So you don't necessarily, this doesn't imply this, but this implies this. And then you have the weaker statement that would be, f of n is n to the minus 5/48 plus little o of 1. So this just means that for any epsilon positive, for any large enough n, f of n is smaller than n to the minus 5/48 minus epsilon, plus epsilon, and n to the minus 5/48 minus epsilon. So for instance, f of n could be n to the minus 5/48 times log of n. That would still hold here. That would still be okay, but so of course, this would be large stronger than this would be stronger than this, and this is the only thing we can prove. But it's okay. I mean, it tells us what the right exponent is. So you can claim that we have the one arm exponent for critical percolation. And really, I don't think we know how to prove this or this, actually. And you will see that why. Well, actually, maybe this is not so hopeless, but... okay, so how do we do this? So we have, for each fixed D, sort of convergence of the discrete exploration to the SLE picture. Right? So in particular, what we know is that for any large R, if I look at the annulus, so let's say 1 here, and this is 1 over R. And I look at the picture, so 1 over R plays the role of delta. 1 over R here. And then if I take, a mesh size delta here, and I look at the probability, so R is fixed, delta goes to 0. If I look at the probability here that there exists, so R large and fixed, and look at the probability that there exists an orange path from here to there. Okay. So this is exactly the probability that the discrete exploration process doesn't close a clockwise loop. Okay. And so it converges to the corresponding quantity for the exploration process. So the statement is that this converges as delta goes to 0 to a function that we may call U of R, which is the probability that for the SLE, that this is basically SLE6 closes no clockwise loop. Before T1 over R. Okay? That's just a statement, for this particular domain of convergence of the discrete exploration process. And we know, and the second thing is U of R is equivalent to R to the minus 5 over 48 as R goes to infinity. That's the other thing we know. Okay? There are two things we can do. The first thing is fix a domain, let delta go to 0, and look at the limits of the exploration process in that domain. And the other thing we can do is, in the continuum limit, let R goes to 0, and then look at the event that we have before. Okay? So note that here one thing we can do in that picture is to take delta to be some negative power of R. We take R very large, fixed, and then we just decide, so there's one remark is that in that statement we can write this, if this would be R to the n, and this will be R to the n plus 1. And this is a mesh size 1. And we look at the probability that there exists one arm going from circle of radius R to the n to the circle of radius R to the n plus 1. This picture is the same as this one for delta equal 1 over R to the n plus 1 or something like that. So if you fix R and let n go to infinity, this picture is just the same picture as this one when you let delta go to 0. It's this picture with mesh size 1 over r to the n plus 1. You let n go to infinity, correspond exactly to let the mesh go to 0. So this quantity here, basically the existence of a crossing between r to the n and r to the n plus 1, when n goes to infinity and r fixed, this goes exactly to this quantity u of r. Okay, let us now look at what we can say about the upper bound. So we have, let us choose epsilon small. Any epsilon small and fixed. Then there exists R0 such that for any r larger than R0, u of r is smaller, or let us write both inequalities. U of r is smaller than r to the minus 5 over 48 plus epsilon, smaller than r to the minus 5 over 48 minus epsilon. So of course you might say we are using something which is, this statement is weaker than this one. Right? We are using something weaker than what we actually know, but it's not worth doing more because later on we will anyway lose precision. So let us just take this, okay? So this is just because of this. Now, we remark the following, which is now, if we look at what we're interested in, is the probability that there exists a path from the origin all the way, in the lattice of mesh size 1, all the way to some large distance. So let's take this large distance to be r to the n, with little n getting larger and larger. Let's take r0. So it's clear that this will be smaller than the probability that for any j in, say, 0, n minus 1, if we draw here r to the j and r to the j plus 1, that here there exists a crossing of that annulus. Right? Because, of course, if you have an orange path that goes from 0, from the origin to here, it has to cross all these concentric annuli. Okay? And because these annuli are chosen to be disjoint, the events in each of the, okay, you have to be precise about, not to use twice what happens on the boundary or whatever. What you get is that this is just smaller than the product from j equals 0 to n minus 1 of the probability of crossing the jth annuli. So this will be r to the j, r to the j plus 1. Okay? So you just do, you decompose this into, this is r0, sorry. This is just, you use the fact that what happens in the different annuli is independent. So here we have actually an inequality. So now, what can you say? We have a product of these quantities, right? And when n, when j gets larger, each of these quantities is going to converge to this u of r0. Right? We know that, the jth number here, when j is getting larger, is converging to something. So now it's just, Cesaro mean-type story. So there are different ways to conclude. One way would be to say, well, you know that the lim sup when j goes to infinity of the probability is smaller than R0 to the 5/48 minus 5/48 plus epsilon. Okay, that's just because it converges to something which is smaller than this R0 to the minus 5/48 plus epsilon. Right? We know that this lim sup is actually u of R0 and that u of R0 is this. So therefore, when you take sum 1 over n of sum of j equals 0 to n minus 1 of the log of these guys, right? The lim sup of this guy, it's just a Cesaro mean story, is this smaller than the log of R0 to the minus 5/48 plus epsilon. Okay. And so this is exactly just telling you that the probability, the products of these probabilities j equals 0 and n minus 1. So the lim sup of this guy is smaller than R0 to the minus 5/48. So this guy here to the power 1 over n. Okay. So, which means, roughly speaking, just that that there exists a constant such that such that for any n the probability that you have this from 0 to R0 to the n is smaller than this constant times R0 to the minus 5/48 to the power n. Plus epsilon, sorry. Okay? So just by decomposing, we know that in each, if the annulus is, has a large enough, aspect ratio, the probability of crossing is comparable to this ratio between the smaller circle and the larger circle to the power minus 5/48. Then just by decomposing, things in successive annuli like this, you get an upper bound in terms of the aspect ratio, the upper bound of the type you want. Okay. So, maybe I was not very clear here, but here this is basically trivial, right? So you just say that this is smaller than this, and each of these terms, when j goes to infinity, converges to something, so in the limit it will be like this something to the power n. That's basically all it is. So, of course, now you might want to say, okay, let's take any rho large. Rho is then between, so then there exists n such that r to the n is 1 and rho smaller than r to the n plus 1. Okay, and we can take, if rho is sufficiently large, then you can make sure one has say n over n plus 1 larger than 1 minus epsilon, and n plus 1 over n smaller than 1 plus epsilon, right? If n is sufficiently large, you get this. So So if rho is sufficiently large, you get this. And so then you conclude that the probability that there exists an open path from 0 all the way to rho, this is smaller than the probability that there exists an open path all the way to R0 to the power n, because rho is larger than R0 to the power n, and so now we are almost done with the upper bound. This will prove that this is smaller than this constant times R0 to the power n times minus 5 over 48 plus epsilon. Okay. And then we just say that this is smaller than c times rho to the n over n plus 1, something like that, minus 5 over 48 plus epsilon. Right, because, well, okay, you just use, and so this will be smaller than constant times rho to the power minus 5 over 48 plus, say, 2 epsilon, something like that. Okay, this is just saying, well, once you have this result, you know about concentric annuli of aspect ratio R0, then you know you have it for, you may choose a little epsilon still, but you have it for all rows. Okay, so you see here that the upper bound is actually simple to derive. Just decompose things into, you know, disjoint annuli, and then look at the limit in each of the annuli and let the aspect, you know, first fix epsilon, choose a very large annulus, let delta go to 0 in each of the annuli, take the product of the concentric things, and if this annulus had been taken, you know, of large aspect ratio, this already gives you the right upper bound. And here, of course, you see that this is where, in a way, you lose the up to constants, right? Because in the Cesaro mean statement over there, you don't have any control about how fast you converge. So what is missing in some sense here is some estimate about how fast you do actually converge to the right limit when you look at the probability of discrete probability converging to the continuous one. So maybe there's something to do there, I don't know. Okay, so, but anyway, here you lose, because of the method itself, you lose something which is stronger than the constant. Okay, so this proves basically the upper bound, which is that this does not decay, like, I mean, the power at which is decay is not smaller than 5 over 48, roughly speaking. Now we have to prove the lower bound, right? We want now to prove, sort of, give a lower bound. We want to give a lower bound for the probability that, let's still use, you know, this R0 to the n. To this quantity when n is large. So here what we're going to do is just use, you know, plain standard FKG story. So imagine that we have defined the following event. Let's call it AJ. Right? I call it AJ, and here we have, this is R0 to the J. This has size 2R0 to the J, and here we have R0 to the J over 2. Right? So we have two concentric circles like this. And we are going to assume the event AJ is the event that there exists a crossing from the small circle to the large one. And there exists a circuit, an orange circuit in the small one, and there exists an orange circuit in the large one. Right, so we ask for three things. Now, of course, by Russo-Seymour-Welsh and FKG, what we know is that there exists a constant C which is positive, such that for any j and for any R0, the probability of A of j is larger than C. Because the probability of having these three things, because of SKG, is larger than the probability to have a circuit times the probability to have another circuit in the smaller one times the probability to have a crossing. Okay. Now, each of these three things is bounded from below by Russo-Seymour-Welsh. That's precisely what we know, right? Because you see the aspect ratio of each of these annuli is 2. Okay. Right? We know that if I give you an annulus of aspect ratio 2, the probability that there exists a circuit here is bounded from below, independently of what the size of the picture is. Now, this is true for the inner guy, this is true for the outer guy, and if I give you now a picture like this, say if this is a part of the circle of radius 2, this is a part of the circle of some radius r, and this is 4 times this rate, the probability that there exists, a crossing from here to here is bounded from below by a constant. Actually, you know what the limit is because of Smirnov, but anyway. So this is bounded from below by a constant. And the probability from having all three simultaneously, because of FKG, everything is, an increasing function of the open sites. The probability of having all three simultaneously is larger than the product of these strictly positive numbers, so it's larger than some strictly positive number. Which is, important thing is that this C is independent of J and R0. Okay. So why are we using this? Because what we want is to take so we have the probability that R0 to the n. Okay. And we want to find a lower bound. So we're going to give a lower bound about this, which is the following, that put it this way. For any j in 0 n minus 1, you have a crossing between R0 to the j and R0 to the j plus 1. Okay. So this is not quite enough. If you have a crossing of each of the concentric annuli, this is not quite enough to create a crossing of the entire picture, because maybe here you have a crossing here, and maybe here you have a crossing here, and nothing tells you that you are sure that these two crossings, you can combine the two. But however, what happens is, if you also say that and for any j in 0 n minus 1, or say 1 minus 1, aj holds. So then that means that basically around, so remember here this aspect ratio is R0. This is very large. Right here where I have R0 to the j minus 1, R0 to the j, R0 to the j plus 1, and so on. Okay. R0 is supposed to be large. So in particular, if I take a look at R0 to the j over 2, it's somewhere here, and when I take R0 to the j, it's somewhere here. Now, if I assume A of j holds, that means that here I have a circuit, here I have a circuit, and I also have a crossing here. So that means, of course, that you're going to be able to connect this crossing here to that crossing here. How are you going to do it? First, go up to this circuit. You You come here, you reach the circuit. You follow this circuit until you hit this little crossing here. You follow here. You reach the second circuit. And then you go around it until you hit this other crossing, and then you continue like this, right? So basically, each time you have a picture like this here, that will enable you, to connect anything that arrives here to anything that starts from here just by, take this, then go around here and get to the other one. Okay. So this is just, standard, simple FKG story. So indeed, we have a lower bound, which is that basically, if all of this happens, then you have a crossing. Because you will be able, to follow all these concentric crossings and to connect them each one to the next one. Now, because of the FKG inequality, this is larger than the product of the probabilities because things are positively correlated. Everything here, are about existence of crossing of orange things. So everything is positively correlated, so it will be the product of these things. So this will be larger than the product of j equals 0 to n minus 1, capital N, of the probability of having a crossing between R0 to the j and R0 to the j plus 1. And here, I have basically this constant here, c to the n minus 1, because I used it n times. Right? You used it. You know that the probability of aj is bounded from below by some constant. Okay. Now we assume what we can. So you see here we lose a little something at each step. We lose a constant. So it might be problematic, but here you note that it's important to note that here this constant that we have here does not depend on R0. Okay. So we could have chosen, R0 large enough so that not only this U of R quantity holds, but also so that the constant C is larger than R0 to the minus epsilon. If you take R0 large enough, it can become smaller than this constant C once you have fixed epsilon. Right? So the entire thing is we fix epsilon, then we know this is true. Then we choose R0, which such that U of R0 is larger than R0 to the minus 5 over 48 minus epsilon, and this holds. Okay. So here we get that this is larger than R0 to the minus epsilon, to the minus n times epsilon, times the product from j equals 0 to n minus 1 of these annulus crossing probabilities. And now it's the same story as before, in the sense that we know that each of these guys is converging to something, and that this something is larger than R0 to minus 5 over 48 minus epsilon. Right? Because U of R was smaller than 1 over R to the minus 5 over 48 plus epsilon. Here we have larger than R to the minus 5 over 48 minus epsilon when j goes to infinity. Okay? So here, exactly as before, we get that this probability here will be larger, or the lim sup, or the lim inf, when n goes to infinity, of this probability here to the power 1 over n will be larger than, so this will contribute to the R0 to the minus epsilon. And here we have the Cesaro mean story that tells you that this is larger than R0 to the minus 5 over 48 minus epsilon. Okay. So indeed, when n large, the probability that we have this picture is larger than r to the minus 5 over 48, say minus 3 epsilon to the n. Okay? So we don't worry about, anyway, we lose an epsilon, so let's lose another epsilon between this step and that step. Okay? So I'm deliberately going very slowly just to show you, that things, if you take the limits in the right order, there's absolutely no problem, So the conclusion, and again, and same, so for large R, and as before, for large rho, we deduce the probability that there exists open path from 0 to rho will be larger than rho, some constant times rho to the minus 5 over 48, say minus 4 epsilon. Right? Or you might say just remove the constant. Okay? Just because we're saying rho is between some R0 to the n and R0 to the n plus 1, and this doesn't affect things by more than a constant in the exponent anyway in the later on. So conclusion, so this finishes the proof. Of the fact that the probability that there exists an open path from the origin all the way to distance rho, that this is equal to rho to the minus 5 over 48 plus little o of 1 as rho goes to infinity. Okay, we have the upper bound, we have the lower bound, we're done. So maybe now is a good time to make the break, because then the question will be, okay, what happens with the other things? With a case where you have 2 arms and when your case you have 4 arms. Then things are slightly more tricky. And if you think a little bit about it, it's quite clear where things will be more tricky. Here, we have used these A of J stories, yes? These guys here. And we made extensive use of the fact that everything, was just increasing FKG inequalities, and you just had to say, well, you see this picture, you see this other picture, you connect these things together, and the inequality goes the right way because of FKG. And this all was working nicely because you had only one color. You were just saying, well, there exists an orange part like this, an orange part like this, things are positively correlated, we're happy. For the other exponents, for the sort of 2 arms and 4 arms and so, we are looking at the probability of events such that there exists an orange path and a yellow path. So here you have to be careful about, what do you do in order to replace this, little intermediate piece in order to make sure to connect, a double 2 arms inside one annulus and 2 arms inside the other annulus in order to connect them together. So we'll see how, I'll try to explain to you very briefly how one can proceed there. And so for those of you who've been to Pierre's lecture already, they maybe remember that there were stories about separation lemmas and things like that, and that this will probably be very helpful here. This is the type of thing that we will need. So FKG doesn't work, so we need to invent something else. Okay, so I guess it's better to make an early break today and then continue. So let's do 15 minutes.